morning, everybody, and welcome to note video number 1 for Unit 8, Momentum. So let's dive right in. One does not simply be productive during spring break. Well, when your spring break is almost 3 weeks long, we are going to try our best. And KD, Kevin Durant, we're going to understand the message of that in just a sec. So let's dive right in. What is impulse? Well, impulse talks about a collision between two objects and that short duration of time where those objects are interacting with each other. All right. And what I mean by this specifically is how long are those objects in contact with each other when they collide. All right. So let's look at an example with a golf ball. So you have a golf ball going towards some hard surface, and notice when the golf ball hits that wall how it changes shape, how it compresses and then bounces off and then goes in the opposite direction. This is what impulse is. It is that compression of that object and the short duration of time that that golf ball is in contact with that wall. All right. So if we were to graph a force versus time graph for the object, for that collision that we just watched, it would look something like this, where right here is where the object begins contact with that wall. Here is where it ends contact with that wall. And this right here is the maximum point of compression, where that ball is compressed the most amount, and that's where it experiences the maximum amount of force. Now notice it makes sense how this graph is shaped. It starts off with not a lot of force, but then over time that force increases till it reaches a maximum and then decreases until the ball is no longer touching that wall. All right. So the more that ball compresses, the larger the force on that ball or on that object. All right. If it's just a quick little collision, there's going to be less force. If it is a longer collision, more impulse, probably going to be a higher force. All right. So impulse is a force exerted over a short interval of time. Now, specifically, it is the area under the force curve. It is the area under the force curve, which means that impulse, which we represent with a J, is equal to the average force delivered to that object multiplied by the time that it is interacting with that object. All right. So if you look at this picture over here, we can see that all of this shaded in area right here is the impulse. All right. That is the amount of force per time that is being delivered to that. All right. Now, we're going to call it the average force because we don't have the tools to calculate the area of this curve right here. All right. We need some calculus for that. We need to take an integral. We can't do that. So what we're going to do is we're going to approximate it with just a little square right here because we know how to find the area of that square. So it's going to be easier to do that. For impulse, it has units of Newton seconds because it's force multiplied by time, or you can see it as kilogram meters per second. Either one of those will be fine. All right, so let's do an example. So we have a rubber ball that experiences the force shown in the graph as it bounces off of the floor. What is the impulse on the ball, and what is the average force on that ball? All right, so looking at this, remember, impulse is the is the area under this curve right here. So we're going to try to find the area of this triangle. That's like as basic as we can put it. All right, so we know that the area of a triangle is 1/2 base times height. All right. Now in this case, the base is our time. The height is our force. All right. So 1/2 times the base, which is the change in time, times the height, which is going to be our maximum force. That's going to be this point right here. That's where our maximum force is. All right. So we're going to replace this with J because J is our impulse and that's our area, is equal to 1/2 times the change in time, which is 8 milliseconds, so that's 0.008 seconds, times the maximum force, which is 300 newtons. And we're going to get that our impulse is equal to 1.2, and then this is newtons times seconds. All right, so that's our impulse that's delivered to this. Now, if we want to figure out the average force delivered to the ball, well, let's go back to our equation here. Our equation, well, we're getting ahead of ourselves here. our equation was J is equal to force average times the change in time. So let's use that. J is average force times the change in time. So if I want to find that average force, I just rearrange and I get J divided by the change in time, which is just going to be 1.2 Newton seconds divided by 0.008 seconds. So I get that the average force is going to be equal to 150 newtons. Now that may seem like a large amount of force, but we have to keep in mind that this is being applied for just a very, very short amount of time. So that average force actually makes sense. So let's talk about momentum now. Now this is that Kevin Durant example at the beginning where you are the real MVP. Well, notice that momentum is equal to mass times velocity. Now we use P to represent momentum because mass is already using M. M represents mass and V represents velocity. Remember, mass has units of kg, kilograms, velocity, units of meters per second, which means that momentum has units of kilograms times meters per second. Pretty easy to remember. With this, momentum and velocity are both vectors, which means they have a magnitude and a direction. All right? Because of that, we can split momentum into components, an x component and a y component, based on the direction of that velocity. All right, that velocity has an x component and a y component as well. So let's talk about this thing called the impulse momentum theorem. Now this is kind of the baseline of this entire unit right here. An impulse delivered to an object causes the object's momentum to change. All right. Now let's think about this with our video example at the beginning. Here, I have a ball moving towards the wall, all right? So its momentum is pointing in this direction. Once it hits that wall, its momentum points in the opposite direction. So we've had a change in momentum caused by an impulse at the wall. Think of impulse like we did with, or I guess we haven't talked about work yet, so I can't use that example. But here is my impulse J. Here is my initial momentum. Here is my final momentum, all right? So that impulse causes that change there. So that's what we come up with this right here. J is equal to the change in momentum, where P final is equal to mass times V final, and P initial is equal to mass times V initial. Now we can combine all of this into this equation, where J is equal to the average force multiplied by the time. So therefore, force average times the change in time is equal to the change in momentum. This right here is a very, very important equation for us, all right? And we're going to use it in an example coming up here. So, since momentum, velocity, and force are all vectors and they are all involved in this equation, that means that impulse J is a vector, which means that we can split it into components. We can have an x component of J and a y component of J based on the direction of that velocity. Now we're primarily going to work with one-dimensional examples, so that's either momentum that's entirely in the x world or momentum entirely in the y world. However, it can be in two dimensions, all right? Therefore, the direction of the impulse is equivalent to the direction of the force. So again, let's go back to this video here. In this example, my ball is moving towards the wall, all right? Now, if I want to change my momentum to the opposite direction, that means that my impulse has to be pointed this way. So if my impulse is pointed this way, that means that my force has to be pointed this way as well, which makes sense. I'm changing my direction of motion, therefore my force needs to point in the direction of the change, all right? So let's talk about how we problem solve with this stuff. Step one, as we've all these steps should look very familiar here. We sketch the situation. We need to draw a before and an after picture of the scenario. We need to establish a coordinate system, define our variables, list any known information, and then identify what you're solving for, as we've done all year. All right, so let's look at that in practice here. We got a 150-gram baseball thrown with a speed of 20 meters per second. It's hit straight back towards the pitcher at a speed of 40 meters per second. The force is given by the graph, And what is the maximum force? So we're looking for this point right here. What is the maximum force that the bat exerts on the ball? All right, so sketch the situation before and after. So if we think about this before and after, initially we've got the bat right here. All right, here's the bat, and we have the ball moving towards the bat. Ball is moving towards the bat with some initial velocity equal to 20 meters per second. Now, this 20 meters per second has to be negative because it's moving towards the bat. So it's 20. The mass of that ball is 0.15 kilograms. All right. And let's say that this right here is our X world. Okay, so here's our X world. And this right here, where the bat is going to contact the ball, that's going to be our 0 point. All right. Now, after the collision, the bat has hit the ball, and the ball is moving in the opposite direction, except its final velocity now is a positive 40 meters per second. I know it has to be positive because it's moving opposite the direction it was at the beginning. All right. Now, what we need to find is we need to find the maximum force. Find the maximum force. All right. So let's dive right in. We know from what we talked about before that the change in momentum in the X world here, because everything's happening in the X world, is equal to the impulse, which we know the impulse is the area under the force curve. All right, this is where we start. Now, my change in momentum in the X world is equal to mass times the final velocity in the X minus mass times the initial velocity in the X. All right, that was this whole situation over here, right? P final minus P initial. So we know what the mass is. We know what the initial velocity is. We know what the final velocity is. So we can calculate what that change in momentum is going to be. The change in momentum in the X is going to be 0.15 kg times V final minus V initial. So this is going to be 40 meters per second minus a negative 20 meters per second. All right. So we get that the change in momentum in the X world is equal to 9 kilogram times meters per second. 9 kilograms times meters per second. All right. So if we know what the change in momentum is, well, then we can calculate some other things from that. Now, I need to get rid of this, so let's clear that off. Maybe. To be honest, this is my first time using this here. Sure, we'll go with this. All right. So here's what we do now. We also know from our previous example that the change in momentum is equal to the impulse, which means that the change in momentum is equal to the average force multiplied by the change in time. All right. So let's look at the impulse here. The impulse is equal to the area under the force curve. Now notice this area is a triangle, which means that this area is equal to 1/2 times the maximum force times the change in time, just like that original example that we did. All right. So I know what the change in time is. It's 0.6 milliseconds. I know what impulse in the X world is equal to because impulse in the X world is equal to the change in momentum in the X world. So let's set these things equal to each other. All right. So I can say that the change in momentum in the X world is equal to 1/2 the max force times the change in time, which means that 2 times the change in momentum in the X divided by the change in time is equal to the max force. So we plug in, we get 2 times 9.0 kilogram meters per second divided by 6.6 milliseconds, which is going to be 6 times 10 to the negative 4th seconds. And I get that my maximum force is going to be equal to 30,000 newtons. 30,000 newtons. All right. Here is what is very tough about these problems, is that 30,000 newtons sounds like a ridiculous amount of force. It sounds way too high. However, that amount of force makes sense for this because we changed our velocity by 60 meters per second in 0.6 milliseconds. In order for us to do that, we would have to deliver a large amount of force. Now also think about this. It only takes about 5,000 newtons to break your nose. So if you think about it, would getting hit in the face by a baseball bat break your nose? Absolutely. And 30,000 newtons says that right here. 30,000 newtons would absolutely do a lot of damage. So conceptually, this makes sense. All right. Thanks, guys. Email me with questions if you have any, and have a great day.